in this lab, you're going to be finding the density of objects. And the density formula, the symbol, I don't know what symbol, I can't remember what the book uses. I think they just might write the word out, density. But the traditional symbol is the rho. So it's kind of like a P. And it's mass divided by volume. So in this particular lab, you're going to be finding the mass 2 different ways, and finding the volume 3 different ways. And then you're going to combine them. So that's what the chart over here is. For example, if you find you get the mass and you get 4 and 6 as grams, or the 2 masses that you got for whatever object it is, and you got 3 different volumes, hopefully the spread will not be that big for when you actually do it. But that last table, table 3, the density, procedure C, you're basically going to take all the combinations here. So where I have M1, V1, you'll be taking, since density, again, is mass over volume, you'll be taking mass 1 divided by volume 1, and that would go here. And that would be grams per cubic centimeter. You know, I don't have units in that chart, so you need to add them appropriately. This spot right here would be mass 1 divided by volume 2. So 4 divided by 9. And then mass 1 divided by volume 3. And then similarly, over there, you'll now take mass 2 divided by each of these, and you get 0.75 grams per cubic centimeter, 0.67 grams per cubic centimeter, and 0.5. So that's how that last chart is filled in. In the analysis, as part of the analysis of these 2 techniques, you're going to pick which technique you feel is the better result. Of these 3 techniques, you're going to pick out which one is the better result. So for number 2, you're picking which one of these. You and your lab partner don't have to agree on this. This is an analysis question. You can obviously discuss it, but you don't have to agree. So problem 2, or question 2, you're picking which of these is the best. For question 3, you're picking which of these is the best. For 4, you're taking the best mass and the best volume, and coming up with the density for number 4. Number 5, you're trying to figure out what the material is based upon some table you look up. 6, you'll do percent error between that value you found in 4 and the value in the table that you find. When I ask for the percent error, typically when you're finding percent error, there's the correct value, and then there is the value that you found experimentally, but you have 6 values here. What I want you to do is, question number 1, how do the 6 densities compare? What's the percent difference between the largest and smallest? When you're doing percent difference, you find the difference between the 2 numbers you're comparing, and you divide by the average of those 2 numbers. I'm asking for something a little bit different here. You take the largest and the smallest, find the difference between them, but this time divide by the average of all 6 numbers. So it's written on there, but the verbal reminder might help. Questions to hear? All right. Sort of going backwards here. One of the ways that you're going to be finding the volume is by formula under V3. Now, I've got 3 spaces here. There's dimension 1, dimension 2, and dimension 3. You're not necessarily going to fill in all of that. If you're doing the rectangular solid, basically you will use all 3. There'll be one for length, one's width, and one's height. If you're doing a cube, you only need 1 of them. If you're doing a sphere, you only need 1, probably the diameter. If you're doing a cylinder, you need 2. So however many things that you have to measure, that's the number of these that you're going to fill in. Questions to hear? All right. When finding the mass, you're going to first find the mass by putting the mass on top of it. This is N1. Just typical the way you've been doing finding mass in the past. For part two, for the second way of finding mass, you're going to dangle it from underneath. Now, some of these already have a string attached to them. You want to tie a string or somehow attach the mass as close to this as possible. This is directly under here. So if you find the mass this way and the string is tied up over here, you're going to get horrible results. So you want the string as close to this as possible. Some people have enough dexterity that they can tie it around that center spot right there, which is great. Some people have to tie it around here and then shift it over as far as possible. Not as great, but you know, it'll do. So that's what the second way of finding mass. Now, if we look at the forces involved, here we have, weight's acting down on it. The Earth is pulling down on it with a gravitational pull, and then there's a normal force holding it up. Here, you have weight pulling down, but this time there's a tension holding it up. When you're finding volume the first way, I believe, the first way, what you're going to do is it's dangling underneath, and you are going to put it in water, completely submerged in water. We have now introduced a third force involved here. We have weight pulling it down, we have a tension holding it up, and then we have a buoyant force holding it up. The buoyant force is equal to the weight of the displaced water. Or whatever the fluid happens to be, but in this case it's going to be water. So, how much water got pushed out of the way? Well, it turns out that the mass of the water that gets pushed out of the way is equal to the difference in this reading and this reading. And once you know the mass difference, well, actually all we need to know is the mass. So once we have the mass of water, we're trying to find volume. The density of water is equal to the mass of the water that gets pushed out of the way, divided by the volume of the water. Well, what's the density of water?
Is it 8 point something? I don't know where I got that from, honestly.
I'm trying to picture some unit system where 8 point something works, but I don't know if you're going with 1,000 what?
Kilograms
Over volume, units of volume.
Units of volume.
Yeah, it's 1,000 kilograms per cubic meter. However, when dealing with density, yes, kilograms per cubic meter is the standard international. However, there are certain traditions that started before the international standard got switched to that. So a lot of densities are in grams per cubic centimeter. So and since we're finding mass in grams, we're finding volumes in cubic centimeters, it's very convenient because the density of water is 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. Because remember, when you're first doing science, you come up with a discovery, you want other people to get the same results you did, so you have to establish some standards. And because water is so plentiful, they established the density as 1 in that particular unit system. So water has for a number of quantities for water, it's 1 in some unit system, just so that it's easy enough to transmit throughout the world. Or at the time it was happening, most likely Europe.
So to use that formula right there that we have up when we're looking for the weight of the displaced water, would we have 1 as our density equal to the mass, which is the mass of this one minus the mass of the other one, because the difference in the masses.
Difference in the masses is the mass of the water.
And then X would be on the bottom. We saw
Yes.
X.
Yes. In essence, if we did the math there, I got 1 is equal to the mass over volume.
Thank you.
Other than units, what's the relationship between mass and volume? Other than units. If mass is 4 grams, what's the volume? Make it way harder than,
Is it just a 1-to-1 ratio?
it is a 1-to-1 ratio, so if that's
4, it has to be 4.
Yeah.
Oh,
if that's 4 grams, that's 4 cubic centimeters.
Oh, yeah, that was.
Okay.
Yeah.
At this point, are there any questions? Then you know what it's time to do,
Rejoice.
because this is physics.
You ready to get these started?
I've got some beakers back there. Oh, logistically, when you're putting the cube into water here, well, you want the cube, you don't want the cube touching the glass at all, so it needs to be suspended in there. It's sometimes helpful, you have this set up, potentially just dangling off the edge like that. And then we have books, or you can put a chair underneath or something so that you don't have to have it dangle all the way to the ground. So we can prop it up. And somewhere we've got basically lifts that we can use. See if I can track those down now. Anyway, continue rejoicing. And are you familiar with the meniscus for the water?
What's a meniscus?
It's the bottom part of the water where it dips
Yeah,
down.
well, basically, water is attracted to the sides, so water's gonna creep up the sides of the glass or plastic tube. And so you have the graduated cylinder,
So like if it's in the beaker during the graduated.
water is going to basically go like that.
And then meniscus.
So when you're measuring, whatever volume you're measuring, be consistent. You can either go for the bottom here, or go for the top, or somewhere in the middle, although I'd recommend top or bottom. Just be consistent in whichever one you use.